Okay, modeling and optimization. I'm giving the lesson now, so if you guys can keep it down. So, fabricating a box. You've done the box problem before. You guys remember the box where you cut out the corner? You might not find it as hard this time. You cut out a corner and you fold it up. And like for pre-calc, I actually make you guys a box, right? So this piece of cardboard is 20 by 25. It's a different size than the one in the pre-calc book. So let's go ahead and figure out what's the volume of this box. So what are my dimensions? What is this height dimension? Or maybe the width of the box or the length.
The shorter one or the
Either one.
one?
No. Remember, I'm folding the sides up. What's the dimension of the actual box? Because I'm cutting out sides of length x, it's 20 minus 2x.
Oh,
What's the other one? Hmm. And when I fold it up, what's the height of the box? X. Okay, what is a reasonable domain for this? What are possible values of x is basically what I'm asking. It's got to be more than 0. What's the largest value x could be? Think about this bottom dimension.
well,
No, it's a little smaller than 20. 10. So x can't go more than halfway if I'm folding it up, right? If I do 20 minus 2 times 10, that's 0. I have a bottom side of 0. I don't have a box at all. I have. So I know my answers have to be somewhere between 0 and 10. You might get a third answer that's just not going to be valid. So we're trying to maximize. Maximums, remember, occur on a graph when the derivative is 0. So it means I want the derivative. This is a triple product rule. I don't want anything to do with that. So I'm going to expand this out.
okay.
Okay? Your calculator's right there.
Yeah. Try to do stats without it. It's not easy.
It's like gonna be like, good luck. 20 times 25 is 500. Um, minus 40x minus 50x plus 4x squared. And now I'll multiply it by x and combine those to be 90. And for the heck of it, I'm going to turn it around because we tend to like this form better. Now, my derivative is pretty simple, isn't it? 12x squared minus 180x plus 500. This does not factor, so you use the quadratic formula. Just what you wanted, right? Can you please convince my pre-calc class that they need to learn how to factor and actually use factoring? Could you convince your younger self of that as well?
I think if I forced my younger self to sit in this class and take that class,
Um,
don't know when it like when we can.
it was like sometime last year.
Yeah, it's still.
So when you get this, you get 2.2 answers, 3.68, 11.32. 11.32 isn't in that domain, is it?
No.
So I want x to equal 3.68. Let's see what the question it says. Okay, how large should the squares be to make the box hold as much as possible? That's this. It then asks you what is the maximum volume. So now I have to do v of 3.68.
I
So notice how I went back and read the problem to see did I answer it.
the derivative was where max.
The derivative being 0 gives me the maximum. hmm Now I have to find y. If you got two of them, you could potentially have a max and a min within your range. You'd need to find y to figure out which one is the maximum. Okay. Also, you'd potentially need to check endpoints. Well, v of 0 is 0, v of 10 is also 0. Okay. This one, I don't really need to check endpoints because cutting out 0 doesn't make any sense. So things though I'd want to do though is I'd want to compare, oops, these three things, v of 0, v of 3.68, and v of 10, potentially. This one, again, 0. You guys both have an Inspire, right? You want to learn a trick for this? Let's learn a trick.
Carrying that big stack of everything.
So, if you do this, we can call v parentheses x. And if you do your colon equal, you can define your function. Colon equals is control of the button next to 9. You could also just enter this into a graph if you wanted, but then it'd be F1. So now I've done that. Now I can just use function notation to get my answers.
Dogs, like we've been doing this the entire time.
So clearly 3.68 is the maximum.
Yeah.
I'll do the other one and you'll see that it's a minimum. We got a negative volume. That doesn't actually make any sense. That's where the domain comes in. Yes, the anti-box. Isn't that great? So one of the keys though is when you're getting volume, use the original, don't use the derivative. Okay. So apparently we lost that work, but that's okay. We're moving on to the next example. The designing a can. You've been asked to design a 1 liter oil can shaped like a right circular cylinder. What dimensions use the least material? Now, a liter does not convert at all to linear dimensions. Well, it does, but you can't have linear dimensions that are liters, right? But you guys know how much 1 milliliter equals in cubic centimeters. A milliliter is a cubic centimeter. So 1 liter equals how many cubic centimeters? Thousandths. Yep. So 1,000 cubic centimeters. This is a volume. So this is my V. We know volume of a cylinder is pi r squared h. That's going to be in the front of your packet. We're trying to minimize material. Material is a surface area. A can has a top and bottom. What are the top and bottom? And it has a side. So this is a cylinder, right? When I unroll it, it becomes a rectangle. This is height. What's the bottom dimension of my cylinder? Circumference of the circle, right? So circumference of a circle is 2 pi r. That's the length. The height is h. So this is my surface area of a cylinder. So now it asks what dimensions will use the least material. So I'm going to plug in, I know the volume. I need to use this to eliminate one of the variables here. I'm going to solve for h, so I only have to plug in once. So that means dividing by pi r squared. So I have kind of a system of equations. And so when I plug into surface area here, I get 2 pi r squared plus 2 pi r times 1,000 over pi r squared. Oh, there should be an r here. So now before I take the derivative, let's simplify. That one of those r's cancels and one of the pi's cancel. And again, before I take the derivative, I'll simplify a little bit. 2,000 over r is times r to the negative first, right? That makes a derivative much easier. So the derivative of surface area. Okay. To maximize, I set it equal to 0. To make solving this easier, I'm going to move the r to the negative second to the bottom. Why do I have an r to the second? I don't know. So right now I have this r squared at the denominator. How do I get rid of an r squared from the denominator? Multiply everything by r squared. So this one, it just cancels. that becomes 4 pi r cubed. And 0 is still 0. So now to solve, I'm going to add 2,000 to each side to move it to the other side. I will divide by 4 pi. And I'm not going to do this to the calculator yet. Then I'll cube root both sides, actually. Cube root, I don't need a plus or minus because cubes can be negative. And now I'll stick this whole thing into the calculator and get R is equal to 5.42. Again, I need to check what does it ask me to? It says what will be the dimensions? Am I done? No, that's one dimension. Dimension 2, and I'll leave space here to write them together at the end. I need H. I have this right here is the easiest form to get H. And that comes out to be anybody, can you plug that in now?
Yeah.
It's like the book doesn't actually show it.
Wow.
10.83 or 84.
Let's fit that.
So those are my dimensions. It does want to verify that this would be a max. You could do a second derivative on this, which would be a bit of a pain, and get that that's a concave down so that it's negative. That would mean it's a max. They do a bunch of that in the book, but so last exam, I think this is going to be our last example for today, is going to be inscribing a rectangle. So we are inscribing a rectangle under one piece of the sine curve. So hopefully from pre-calc you remember that a sine wave looks like this, right? And we're inscribing a rectangle here. We're trying to maximize that area. So I'll draw it a little bigger here. We know that this is 0, 0. We know that the sine returns to 0 at pi. Okay? So we know that this here in the middle is pi over 2. So we're going to call this coordinate here x 0. This coordinate here is then x sine of x because its y coordinate is the sine of it. That makes sense? So if I'm doing length times width, my width of this is sine x. That's this vertical height on the triangle.
Oh, the,
My length here, if I do the halfway part, I can do this two different ways. The total thing is pi, right? This distance here is x, and it should be symmetric, correct?
uh,
So length is equal to pi minus 2x. I'm trying to maximize my area, length times width. I could take this derivative using the product rule. I could also just graph and find the maximum, right? I could take the derivative using the product rule. I probably couldn't solve that derivative function equals 0. So we're going to go ahead and just graph this. So we grab a graph. Okay, I'm in radian. You pretty much always need to be in radian for graphing and definitely need to be in radian for calculus.
uh,
Keep in mind that x has to be less than pi over 2. So I don't need to really see all of these things. If you want, you could take your window, 0 to and all my legitimate do you see how understanding that idea of legal domain here or reasonable domain becomes important? 0.7105 is x. So it's about halfway in between. If you really wide, you got a wide but not tall. If you get towards the middle too far, you get tall but not wide. And you're trying to find the maximized balance. That makes sense? That is optimization. The hardest part is setting it up and getting the equations together. Usually the derivatives are not that bad.
seems